Hi, I'm Gavin Wince, and today we're going to be talking about the Existics equations in depth. About 15 years ago, I started promoting Existics online, making predictions, presenting the mathematical formulas for what then was considered very speculative mathematics. What's happened since, though, is that several of the predictions that I made with these mathematics have not only been observed experimentally, but there are no current theories or mathematical formulas to account for these observations. I have something I'm going to read here before we get started. What is existics and what makes it important? Existics is the study of the laws that govern existence. It's more fundamental than physics. Physics is the study of the laws that govern physical reality. However, there are other aspects to existence physics doesn't cover. So is existics some kind of a metaphysics then? Oxford defines metaphysics as the branch of philosophy that deals with first principles of things, including abstract concepts such as being, knowing, substance, cause, identity, time, and space. Essentially, the study of reality. Physics, therefore, is a special case or subset of metaphysics, given physical reality is a subset of all reality. However, we can argue existics is even more general, given that all of reality is a special case or subset of existence. For there are things that exist that are not part of our complete reality. To demonstrate existics as a more general formalization of fundamental laws, we will focus specifically on the mathematics of physics. I will now use the formal language of existics, expressed in mathematical form, to derive the fundamental mathematics used in physical law and demonstrate where modern physics fails and the existics applications to physics succeeds. So let's go ahead and go to document number 1. So this is a document I put together in September, titled Existics, Fundamental Equations and Expressions, and we're going to go over the contents briefly. So what we're first going to do is we're going to do a basic introduction and go over the basic formalization of the equations. Then we're going to give an example of solving the equations, and this example will come in significantly towards the end. Then we're going to connect the existics equations to the Pythagorean triples, which basically means that you can use the existics equations to derive right angles. Then we're going to use a closed form expression for the telescoping sums, which leads us into a calculus-style recursion summation series for n star and u star. Then we're going to go to differential equations for existics summation series for n star and u star. Then we're the definite integral for identity transformation over time. Then we're going to derive three-dimensional time from the existics recursive arithmetic. Now I'd like to say something real quick here. There are not very many people dealing with the subject of multidimensional time. As a matter of fact, if you go to Google and you make the search so that you only go from 2001 up to about 2020, you'll find that I'm the only person speaking about three-dimensional time. There's a couple other individuals like Roy Herbert and Itzhak Bars and a few others, but it's a very elusive, kind of abstract area, and a lot of the other people that are dealing with multidimensional time don't actually have a justification for how they came to it. It's sort of like an idea that was inspired. Ironically, the way I came to three-dimensional time was by deriving it as a necessary way to account for temporal phenomena. So we'll go ahead and go back to the document. After we define the three dimensions of time, we'll then get into the inverse relationship between periods and passage. Then we will apply the existics equations to imaginary numbers. We'll then derive quaternion mathematics from that application. We'll derive the unitary evolution operator for recursive existics time steps. We will use recursive expressions to resolve self-energies without renormalization. We'll show how quantized spin derived from existics recursive arithmetic is possible. We'll show a former operator, algebraic, and Dirac evolution equation from existics recursion. We will then get into the formalization of physical law derived from the existics equations. And then the grand finale is the formal derivation, recursive identity, and the fine structure constant. Now, that's something I like to speak to this. This last section that we'll cover is extremely significant because what ends up happening is by using the basic existics formulation, I'm able to derive the fine structure constant and several other constants in nature all together as a cluster, showing that not only can these numbers be derived with the existics equations, but rather the existics equations reveal a deeper structure, a deeper mathematical structure as to why these constants show up in nature in the first place. All right, so we'll go ahead and go into the introduction. The existics equations form a novel class of recursive arithmetic relationships that define a structured, convergent process of identity transformation that maps directly onto foundational structures in modern physics and mathematics. Below, we outline significant and unique properties of these equations as a formal treatment of a new subject of mathematical study. Basic formulation. Fundamental relation projections. In existics theory, identity is not treated as an absolute scalar quantity, but as a relational projection between two identities, an observer A and observed system B. The most elementary expression of this projection are defined through dimensionless ratios, forming the basis of all higher recursive structures in the framework. So the forward projection, N. This represents the forward-facing projection of identity, where the identity of A is expressed relative to B. It defines a reference frame in which A is situated as the projecting observer and B is the referenced background. And as you can see, N equals A over B is just your standard, inverse relationship. This foundational form of direct identity expression, the strength, presence, and measure of A as seen through the scalar resolution of B. So now we do the reverse projection. U equals B over A. This is the reciprocal frame where B is projected through the reference scale of A. It provides the reverse viewpoint of how the observed system B manifests when framed in terms of the observer A's identity. So notice we have N equals A over B and U equals B over A. And I selected using N and U because they're sort of reverse symbols of one another. It is always true that N equals 1 over U and U equals 1 over N. This reciprocal symmetry between N and U encodes the bidirectional nature of all relational identity. The observer and the observed are mutually defined through inverse proportions. So now we'll get into building the existics equations. N reflects how much of A fits into B's scale. U reflects how much of B fits into A's scale. Their product always is N times U equals 1. This defines a symmetry of relational equivalence, a key principle in existence. Identity is always expressed in relation to something else, and every reference frame is simultaneously and observed from another perspective. Infinite relative frames of reference. In real interactions, entities exist in nested relative frames of reference where identity in measurable recursive, where identity in measurable, let me start over. In real interactions, entities exist in nested relative frames of reference where identity is in a measurable where identity is measurably recursive. So here we define n star as n equaling a over b plus a over b plus a over b plus a over b ad infinitum. Now something I want to speak to this. The reason why I created this recursive arithmetic had to do with the idea that if one observer is making an observer of some system, and that system exists relative to that observer, then that system relative to that observer also exists relative to that system, and that also exists relative to the observer ad infinitum. Basically, it's almost like when you hold up two mirrors together and you get that reflection that goes back and forth and it infinitely sequences out. So what the recursive arithmetic is capturing is that infinite recursive sequencing of a reference frame within a reference frame within a reference frame ad infinitum. Now, when I first set out to do these equations, I was discouraged because I was told these equations will never work. They'll always diverge to infinity, and so on and so forth. Ironically, though, the thing that makes the Existics equations unique is that they don't diverge. They actually converge to very specific numbers. So we'll go ahead and go back to the document. And so what we're going to do is we're going to go ahead and show that each of these steps in this recursive equation represent a different. So n naught would be the first iteration of a over b. n1 would be the first iteration plus the second. And then n2 would be the first iteration plus the third, etc., until we go down and define that n star equals the limit of all n sub n's. And then here's a telescoping series expression of the same equation. This reflects the expanding nature of the recursion. Each step adds a proportional diminishing increment as the identity of A is recursively projected through a deeper frame of B. So same thing for B, but because B is a reverse projection, we have a minus sign inside of here instead of an addition. So it takes on essentially the same form, but with a minus sign. And so here we can see U star equals the initial U plus the summation of all the subsequent little pieces that are subtracted from U naught. This reflects the contracting structure of reverse recursion. The identity of B folds inward through recursive references to A, and the difference between successive terms shrinks with each step. So now we get what I call the identity constant. Now, obviously, this isn't a constant in the sense that it's a fixed number, but it's a constant in the sense that for any n star and u star, there is a very specific identity constant that goes with those relations. This scalar product encodes the recursive coupling between A and B and represents an invariant of identity space across recursive depth. This can be simplified algebraically, and if you look right here, this is probably the most important expression that has ever come out of Existics, and that is that the ratio The original ratio of A to B is equivalent to the ratio of n star minus I and I star minus, and I minus U star. And what that means is as the gradient of A and B increases, we maintain a right angle and we're able to have invariance. So something I want to speak to on this. In physics, invariance is the concept of maintaining right angles. If you look behind me, you'll see that in order for me to have a three-dimensional time matrix, I have to have all the different dimensions of time oriented at 90 degrees. That way I can treat these as components or legs on a triangle or parts to a vector or parts to a tensor, so that as I come out this direction, the sum of all the parts equals this vector. So invariance is important because if we weren't able to maintain 90 degrees, we wouldn't be able to use the Pythagorean theorem to use the base and the run to calculate the hypotenuse. And it's pretty amazing how much of physics actually is reliant on the Pythagorean theorem. But the main reason is for maintaining invariance. So back to the document. So now what we're going to do is we're going to calculate for A star and B star. So what ends up happening is if we play algebraically with n star and u star, what we're able to show is that n star actually equals a over b minus 1 and u star equals b over a plus 1. Once I was able to derive this from the recursive equations, that's when I knew for certain that they would always converge to a finite number, with the exception of when b equals 1, that being the one exception to the rule. All right, so here you can see I'm just carrying out algebraic expressions to show different formulations and ways that these variables go together. Just continue on that. And again, this is just showing the equivalence that n star minus I over I minus u star has the same ratio as a over b, which is very important. This equation represents a deep invariance condition in the Existics framework. It shows that the apparent asymmetry in forward and reverse subjective time is balanced by the identity product I restoring objective ratio. All right, so here's one where we're going to test the rules and see what happens if we let A equal B, but use the same structure of the equations that we derived. And we just continue to go through this algebraically. Continuing to go through it algebraically. And what we're able to do is prove that even when A over B equals 1, n star minus I over I minus u star also still equals 1. Here being the one exception to the rule, B can never equal 1. Some more algebraic expressions demonstrating that. Okay, so now we're going to solve for A star and B star. So something I want to speak to this. So where these equations originally came from was a conversation I had with my great-grandmother when I was a teenager. And what it was is at about age 16, it became apparent that time was going by faster at 16 than it did at 5 years old. So I was curious, does that phenomena keep happening, right? So I asked my grandma, does time go by faster for you in your 90s than it did when you were like my age? And she told me that time went by so fast for her that she could see the grass grow. Now, obviously, that was a metaphor, but it got me thinking, if time really does go by differently for people, then how is it that we can have an interaction that makes any sense? For instance, if I'm talking to my grandma and time's going by slower for me than it is for her, how is there coherence in that conversation? So where Existics came from was trying to resolve this. And ultimately what I came to is that, all right, there has to be a frame of reference for grandma that's faster than a frame of reference for Gavin. And in Gavin's frame of reference, there's a grandma relative to Gavin. And in grandma's frame of reference, there's a Gavin relative to grandma. And that grandma relative to grandma and grandma relative to Gavin are two different versions of grandma experiencing two different rates of the passage of time. And Gavin relative to grandma and Gavin relative to himself are also two different Gavins, one relative to grandma, one relative to himself. So what the equations are designed to do is, given that they are along two different timelines, where are they in relation to one another on those separate timelines? So what the Existics equations show is, when Gavin's 16 years old, having the conversation with his 90-year-old grandma, when he reaches a certain point in the conversation, she's this far into the future. And then relative to grandma, when she reaches that same particular point in the conversation, Gavin's off into the past, not having caught up to where the conversation's happened yet. And what's beautiful is that the equations, by maintaining invariance, were able to show that this necessitated treating time multidimensionally. All right, so we'll go back to the document. All right, so solving for A star and B star, in this case, A would be grandma at 100 years old. A star would be where grandma is in relation to B. B star is where I was in relation to my grandma, and B is where I actually am at. So here's just some more algebra, playing with the equations to derive how do we solve for A star and B star. And then what we end up with down here is our example, right? So let's pretend grandma was 100 years old at the time and Gavin was 20. So first thing we need to do is find n star. So we solve for n star. Now we need to solve for u star. Now we derive the identity constant by multiplying n star by u star. And now we solve for a star. And a star is nothing more than a plus the forward projection. And b star is nothing more than b minus the reverse projection. And so what we end up with is that with this particular example, if grandma was 100 and Gavin was 20, grandma would be experiencing time 5.263 units of time faster than Gavin, or Gavin would be experiencing 0.198 units of time relative to 1 unit of time of grandma. And so basically, what you have here is at the point of Gavin and grandma being in proximity to one another, and grandma's 100, relative to her, Gavin is only 19.15 years old, so he's still got some time to catch up. But when Gavin becomes 20 and has the conversation with grandma, she's actually 104.25 off into the future. And then this is a nice gradient map to show the normalized identity ratios of A star over B star. All right, so something I want to speak to this. So when I created these equations, my intent was to resolve this curiosity through the conversation I had with my grandma. I never had any anticipation of applying this to physics or anything like that. This was more of just a sort of a word puzzle problem I solved over the summer when I was young. So finally, when I get into college and I learn special relativity for the first time, this is when I'm learning there's actual real world scenarios where people can undergo different rates of the passage of time. But what was stunning and what I found a little strange was that the very aspects of what Existics does by accounting for where people would be in relation to one another along separate timelines, neither special nor general relativity did that. So I made the mistake of showing my professors my equations and thinking that somehow they would appreciate it. And that began the beginning of basically me struggling to teach Existics for the past 30 years. So back to the document. So now we're going to connect the Existics equations to the Pythagorean triples. And the reason why this is important is this is basically a geometrical proof to show that the equivalence principle in the Existics equations always derives a right angle and therefore can be used for invariance. So what we're going to do, and here's your basic Pythagorean theorem of x squared plus y squared equals z squared. And here's the Existics equations being brought in into a triangular form to test it. Here's the Pythagorean theorem. All right, so let's start with the most famous of all the Pythagorean theorems, the 3, 4, 5 triangle. So we'll have our rise and our run be 3 and 4. So we'll go ahead and calculate n star and u star. We plug those in. And what do we get? We derive the hypotenuse as being 5 squared. So in this example, we were able to show that the Existics equations maintain the Pythagorean theorem with those numbers. So then we do the same thing with the 5, 12, 13 triangle. We can show that it maintains the same ratio. And then we do the same thing with the 7, 24, 25 triangle. Same thing. Checks out. So basically the key insights is that the Existics identity equation maps directly to the slope of a right triangle. The legs of the triangle, extension and retraction deltas, are pure functions of time asymmetry. The multiplicative, oh my God, I can't talk. The multiplicative identity constant, I, plays the role of an invariant temporal projection anchor. Any valid Pythagorean triple, A, B, C, where A is greater than B, will perfectly satisfy this identity. As a perfect symmetry, A equals B, N star equals U star equals I equals 1. And so the only time that this doesn't work is when all of them equal 1, but you can't form a right angle where all sides equal 1. So there's a table showing that we can do the Existics equations to maintain the right angleness of the Pythagorean triples. This relationship shows that observer asymmetries in the experience of time, when modeled with the recursive Existics structure, map directly onto geometric invariants like those found in Pythagorean right angles. This bridges temporal experience with Euclidean geometry, recursive identity with slope of space-time projection, observer ratio, triangle leg ratio. Thus, the Existics temporal identity equation is a generator of Pythagorean structure and geometrically maps recursive cognitive time differentials onto the unit circle and identity-preserving right triangle ratios. All right, so here we do the closed form expression for the telescoping of sums. And what this ultimately demonstrates is that the Existics equations, even though they can be expressed in this recursive form or telescoping sum, ultimately reduce to this very simple algebraic expression. Same thing for B. All right, so now calculus style recursive summation for series for n star and u star. So here, what we're doing is we're trying to basically bring the existics equations into the mathematical formalization of calculus. So notice right here, this converges towards the fixed point n star, the forward recursive identity. And then this also here converges to the reverse recursive identity. We keep going algebraically. And so here again, we see that same summation that we had at the beginning. And this summation is nothing more than collapsing this telescoped version of the recursive arithmetic into a summation form. We do the same thing for B. And so then, now we have the summation of series form. We're ready to go ahead and move in. This is a linear algebra exercise, and now we're going to move into calculus. These expressions not only reflect converging identity projections, but also highlight how temporal recursion in existics can be approached through the lens of calculus-style iterative methods while remaining purely algebraic in its origin. So notice, typically, to do something like what the existics equations, you'd have to get into this type of a formulation, yet when you carry it out, it reduces to this simple algebraic form. And that's one of the uniqueness of the existics equations, is both their complexity and simplicity at the same time. So now we're going to do a differential equation for the existics equations. We'll go ahead and take the derivative of n in relation to t. Do the same thing with u. Derivative of u with relation to t. And basically, even when you run it through a calculus formalization, you still end up coming back to the basic algebraic form. So what this demonstrates is there are situations in physics where we could skip using summations and definite integrals and just use the basic algebraic structure of the existics equations. And that's actually pretty profound. These show that the recursive arithmetic of existics can be translated into a continuous dynamical system where the function of t to n and the function of t to u flow towards their identity fixed point under time evolution. So now we'll do the definite integral, and I'm sure at this point you can guess what's going to happen. And that is when we take the definite integral of n with relation to t, we just end up right back where we started with the original ratio of b over a or a over b. So again, this demonstrates that the existics equations have a much more subtle and fundamental approach to recursion than using calculus. In fact, for about something I'd like to speak to, there was quite a period of time while I was in college where I kept trying to force my equations to match calculus, and it only took to about the age 50 that I realized, what am I doing? These are the calculus equations can reduce to the existics expressions. So once I realized that, that's when I realized that I really needed to dive deeper into, okay, if I can derive basic calculus using the existics equations, then what is it about the existics equations that make them so unique mathematically? So we'll go back to the document. First, before we get into the significance of the equations, what I'd like to do is let's go ahead and get into deriving three-dimensional time from Existics recursive arithmetic. Now, I've already mentioned that the fact that I can derive a right-angled triangle with the Existics equations demonstrates that there's more than one time dimension. When you really push the Existics equations further, what they demonstrate is actually no, there must be three dimensions of time for these equations to operate within. So the foundational insight, shared present, distinct periods. In classical physics, simultaneity is often treated as a relative or frame-dependent phenomena. In Existics, we uncover a deeper structure. Two identities, A and B, may share the same present moment for a given temporal event, yet experience distinct rates of temporal passage. This insight follows directly from the Existics recursion, where identity frames, defined by A, B, and their projections, N star, U star, and I, exist simultaneously in a recursive structure but maintain asymmetric passage rates. This implies A and B can coexist causally, yet differ in how much their temporal period is consumed per unit of shared present. The present moment thus becomes a dimensional invariant, not merely a coordinate in linear time. So the present moment is just not a point on a line, it's actually a square, it's an area. The present moment as a temporal coordinate. In traditional physics, time is treated as a one-dimensional parameter. The present is assumed to be an infinitesimal derivative of a point along that timeline. But Existics suggests the present moment is not just an infinitesimal slice of a timeline, it is a dimension in which multiple temporal entities, A and B, can co-reside while experiencing different rates of temporal evolution. All right, so let's go ahead and cut to this image behind me. Now, right now, I am in a three-dimensional space, right? And I'm going to show it to you. So you can see we have over here present moments, right? And then over here, we can see we have the periods of time. Go ahead and cut back to me. And over here, we can see we have the periods of time. So along the periods of time, you can see that each one of these lines represents a different period, right? But each of these lines across here is a different present moment. So in this way, the present moment is literally, there's one present moment, there's another present moment. So you have series of present moments along a period of time. So the arrow of time then in this situation would come directly out through the middle, and what you would have is a two-dimensional plane of periods per present moments, and depending on the slope angle of that line would be the rate of the passage of time. So let's go ahead and cut to video 1 just to give a little bit more explanation into that.
Let's suspend everything we know about time for a moment and use our imagination, if you will. Let's allow time to be a two-dimensional vector running in the direction of the arrow of time. We can assign this t1 coordinate to periods of time, and we can assign this t2 coordinate to present moments of time. If we allow the arrow of time to slide more towards the periods of time coordinate,
time moves by faster with more periods per present moments.
Or, if we move the arrow of time more towards the present moment coordinate,
we get more present moments per periods of time.
If we move the arrow of time so that it runs perfectly parallel with the periods of time coordinate, we end up with the past, present, future within a single moment. Or, if we run the arrow of time so that it runs perfectly parallel with the present time coordinate, we end up with an ever-present moment in a single period of time. The concepts of ordinary time and time dilation found in physics have equivalences in three-dimensional time which can easily be accounted for. Temporal events that happen on this side of the arrow of time correspond with the Lorentz transformation, where temporal events on this side of the arrow of time correspond with the inverse Lorentz transformation.
All right. I kind of want to leave it on that image there for a second. Go back to the three-dimensional. There we go. So look at the center point of the three arrows and imagine that center point coming directly at you. That would be time. But what this graph represents is that I can take that and I can bifurcate it into three different dimensions so that I have more ability to quantify time by having extra parameters. For me, three-dimensional time is not really a complicated subject. The people that I find that have the most trouble with it are hardened physicists who've spent a lifetime only thinking of time in a singular dimension. The irony with that, though, is if I'm treating time multidimensionally, I can treat it as a vector, and as a vector, you can think of it as singularly dimensional. All I'm doing is adding extra parameters to time so that I can take that singular time dimension and open it up to bring in more physical phenomena that's not been accounted for yet. So the present moment as a temporal coordinate. In traditional physics, time is treated as a one-dimensional parameter. The present is assumed to be an infinitesimal derivative point along that timeline. But Existics suggests the present moment is not just an infinitesimal slice of a timeline. It is a dimension in which multiple temporal entities, A and B, can co-reside while expressing different rates of temporal evolution. Why? N star minus I and I minus U star describe period deviations, not instantaneous differences, yet both are calculated at the same event within the same present. Hence, the shared rate of change, derivative moment, becomes a frame invariant projection point. This leads to a crucial reformulation. Time, as traditionally defined, is insufficient to capture systems where identity projections coexist in the same present but evolve through different periods. We thus require at minimum one temporal axis for period, cyclic or identity-driven interval, or one temporal axis for present moment, instantaneous co-locations in a causal frame. Their ratio defines linear passage. So again, this period per present moment would be like a line cutting through that two-dimensional plane. Or in Existics, T3 equals T1 over T2, or T3 equals 1 over I, depending on perspective. And so what T3 becomes is the scale factor, or the third component, that can change the rate of the passage of time independent of the ratio of T1 to T2. This explains the curvature of time, not as a warping of space, but as a relational asymmetry in identity recursion. External physical dynamics modulate passage. In relativity, external forces, gravity, velocity, alter the rate at which time passes. In Existics, the scalar identity constant, I, governs passage. Thus, if external conditions modify the recursive structure, they directly alter I and therefore T3. This suggests there exists an external degree of freedom that modulates the rate of change of identity recursion and thereby modulates the rate of change of time itself. This is not merely a rescaling, it's a transformation across a temporal manifold with effects on causal structure, duration, and evolution. So what you can think of is any kind of curve or line that comes out of this three-dimensional time model. What that does is it basically just gives more ability to describe time with more detail because you have these extra parameters to wrap around it. All right, back to the document. All right, so these define a three vector in a temporal identity manifold. So what this shows here is I can just treat time as a vector, bringing in all three components and applying the existics equations to those three components. This structure is not symmetric due to a directionality of identity projection. Is frame relative, each frame observes different passage, respects shared simultaneity, shared present moment, namely because they're along a trajectory rather than a singular point, and supports dynamical curvature, modification of external context. Thus, the existics identity recursion naturally requires and constructs a three-dimensional temporal space. So back to me. So I didn't just one day say, you know what, I think I like the idea of 3D time. I'm just going to go ahead and assume time is three-dimensional. No, what happened was I created a form of equations that through my attempts to understand the significance of them, what they revealed to me was that by applying them to time, the only way they could make sense is that time had to be multidimensionally, specifically 3. Generalization and physical meaning. The full implications are one-dimensional time as a scalar is inadequate to describe systems of interacting identity. Two-dimensional time, period, and moment captures causal simultaneity across distinct temporal rates. Three-dimensional time with passage captures the flow and curvature of identity through time. Moreover, the third temporal dimension is computable and modifiable. In fact, external fields or forces can curve T1 and T2. Internal identity recursion determines I. The observer-dependent flow of time, T3, becomes a measurable projection. Conclusion: time is not singular. It is a structured, recursive, directional manifold that emerges from identity projections. Existics provides the arithmetic mechanism to define T1, T2, T3, the causal consistency to preserve the shared present, the recursive dynamic to encode asymmetry, the scalar passage via I that behaves analogously to both proper time and Lorentz transformations. Thus, three-dimensional time equals present moment plus period differential plus scalar passage, all derive from first principles using the existics recursive arithmetic. So now what we're going to get into is a discovery by applying three-dimensional time to physics. And that has to do with an inverse proportional relationship between the passage coordinate and periods of time. The existics recursive structure defines two identity-related differentials that correspond to distinct temporal period curvatures: forward differential, identity expression, or reverse differential, identity contraction. These two expressions encode the temporal differential geometry of the recursive identity, where the rate of temporal periods between two identity frames is denoted. So here we have the slope of T1 over T2. The key insight is both n star minus I for the expansive identity, and I minus u star for the contraction identity are expressions of the same temporal ratio, T1 over T2, but under opposite curvature conditions. When T1 over T2 is greater than 1, it corresponds to n star minus I. When T1 over T2 is less than 1, it corresponds to I minus u star. This gives a unified identity dynamic interpretation of the temporal curvature space. So we will let T1 be the intrinsic temporal period of the observer frame associated with A star, and N star. T2, the intrinsic temporal period of the observed frame associated with B star, and U star. We define the temporal period ratio as R equals T1 over T2. And then here's our basic conditions and our expression and so on and so forth. So now we'll do the interpretation of period and passage coupling. The scalar identity constant I equals n star times u star governs passage. If measured from the perspective identity expression, the passage is T3 equals 1 over I. If measured from the contraction side, passage is just simply I. This scalar passage relates to the period differential via period differential times passage equals the identity ratio. Thus, for the temporal expansion times T3 equals A over B, the system is expanding with slower passage. For T contraction of B over A, the system is contracting with faster passage. So in essence, thus for the identity expansion, we use n star minus I, and for the identity contraction, we use I minus u star. And so now, temporal period curvature and inequalities. Since both the temporal expansion and the temporal contraction are scalar projections from the same identity recursion, we get this inequality. These are not independent regimes. They are two orientations of the same Existics recursion logic. Together, they span the bidirectional 3T time plane where T1 and T2 are orthogonally or perpendicularly intrinsic. The ratio T1 over T2 encodes the curvature. The passage factor is the depth or flow velocity between them. So here we just put all this into a table. All right, so the physical meaning. Physical meaning. This curvature structure mirrors effects seen in relativistic time dilation. Faster motion, larger T1, results in slower observed passage, smaller T3. Gravitational curvature, clocks in a gravitational well are observed to have fewer periods, smaller T1, per present moment with an elongated passage of time, or larger T3. In both interpretations, passage rate is inversely proportional with periods of time differently, and Existics provides a discrete algebraic model for this. So what this basically means is that this vertical component passage here has what's called an inverse proportional relationship with periods right here. What that means is that if I had a triangle here, as the periods get longer, the passage gets shorter. So they have an inverse relationship here. So if I have a long T1, I have a short T3. If I have a long T3, I have a short T1. And this is very significant because this is where it shows how relativity actually works. Why is there time dilation? And something interesting about relativity, a lot of people think about space contraction, but few understand that if you actually look at the equations, you'll see that it's the time component that's always that is always what brings curvature in. So if time is what allows for the curvature of space-time, then maybe we should be looking at the relationships in multidimensional time components to see if that reveals to us why there's time dilation. All right, so let's go back to the document. Okay. Conclusion: the temporal differentials of n star minus I and I star and I minus U star both describe the same period ratio under two different curvature regimes. This duality reveals that temporal curvature, as derived from recursive identity, This duality reveals that temporal curvature, as derived from recursive identity, is inherently directional, reciprocal, and non-symmetric, and it provides a natural algebraic basis for modeling time beyond one dimension, as required by T3 theory. And one thing I will say that's very interesting about this is that the natural asymmetry between A and B is the reason why, though we have a multi-dimensional time model, time flows in one particular direction. All right, so what of this, right? Did I make any specific predictions about applying three-dimensional time to, say, special relativity to see if there were some predictable observables that could be made? Or if maybe I could falsify these equations and just end this thing altogether, right? Let's go to video number 2.
However, there is an unaccounted for aspect to this paradox, given that Alice and Bob exist in mutually exclusive relative frames of reference undergoing different rates of the passage of time. Since Alice and Bob measured different rates of the passage of time, the rate was slightly faster relative to Alice and slightly slower relative to Bob. Unbeknownst to Alice and Bob, Alice exists slightly into the future relative to Bob, and Bob exists slightly into the past relative to Alice. While in transit, Bob's rate of the passage of time decreases relative to Alice, though Bob eventually decelerates, returning to his original temporal frame of reference contemporary with Alice. Alice and Bob still exist along separate timelines running parallel but staggered in relation to one another. This shift in timelines between Alice and Bob is unaccounted for by the Lorentz transformation. Using the Lorentz transformation for his calculated arrival time, when Bob returns, he apologizes, saying,
"Sorry I'm late."
However, using the Lorentz transformation in her calculation for Bob's arrival time, Alice looks at Bob with astonishment and says, "Oh, you've arrived early." Yet, if we apply the basic Existics equations to the Lorentz transformations, this slight variation in relative time can be accounted for, hence the adjusted twin paradox. Since Lorentz transformations use only one time dimension, if time is multidimensional, anomalies like the ones mentioned above should arise experimentally.
Merging neutron stars explode spectacularly. In GW 170817, the flash of gamma radiation arrived 1.7 seconds after the gravitational waves.
The electromagnetic signal was detected beginning at about 1.7 seconds after the gravitational wave event began.
All right, so what you saw there was a clip from 2014 where I basically lay out a scenario where if the Existics equations are true, then by using the standard physics equations, we should have a situation where a particle or a beam or something appears to arrive early from one frame of reference and late from another frame of reference. Well, in 2017, we had that finally happen. Let's go ahead and go to the document. All right, Wince's 3T prediction of the cosmological crisis prior to observation. On March 16, 2015, Gavin Wince published the documentary The Perfect Cosmological Principle, Return of the Steady State Universe. In the video, Wince uses dimensional analysis to present equations demonstrating that by using a three-dimensional time model, light can propagate through space and redshift without changing its momentum or null effective mass. He constructs his argument around assuming periods of time have an inversely proportional relationship with passage of time, such that, as an alternative interpretation to the Doppler effect, three-dimensional time can be applied to frequency, wavelength, and the speed of light successfully, accounting for the cosmological redshift. What about the idea of an expanding universe? Rather than accelerating, the universal scale for different rates of the passage of time is inversely proportional to the history of the universe. The difference in rate of the passage of time between the 0-point energy and the vacuum energy density corresponds with the age of the universe. If we extend our temporal model and let the energy density of the vacuum correspond with a very high rate of the passage of time, since it is associated with infinitesimal mass, it can be associated with the infinite momentum frame. More towards the center of a galaxy, relative to the gravitational field, there is a significantly slower rate of the passage of time. The rate of the passage of time relative to intergalactic space is at a higher rate of the passage of time. Quantum fluctuations relative to some internal frame have various rates of the passage of time that decreases over an extended period of time. Different rates of the passage of time between 0-point energy and the vacuum energy density can be used to explain away the vacuum catastrophe. We can reinterpret the scale factor in the cosmological equation of state, or the Friedmann equation, and apply it to three-dimensional time rather than 3 dimensions of space. We get a range of different rates of the passage of time over various periods of time per present moments spanning the history of the universe, or in other words, a more properly defined concept of timescapes. Pending any observation that demonstrated multidimensional time, these were mere speculations at the time based off of simply applying the Existics derived three-dimensional time model to cosmology. And something I want to say real quick. When I first started presenting these equations to physicists, mathematicians, professors, you name it, what they said was there are no experiments anywhere near online that can verify any of this. This is just speculative mathematics. Fun, neat ideas, but it'll never be proven. Ironically, in 2017, we had a merger event where gravitational waves were detected 1.7 seconds prior to the accompanying electromagnetic frequency. So just like I had predicted, something arriving early, something arriving late. And that wasn't the only one. Back to the document. So on August 17th, 2017, the Advanced LIGO and Advanced Virgo gravitational wave detectors made the first observation of a binary neutron star inspiraling dubbed GW170817. And I love how it has my initials in it. This was the first time astronomers observed a cosmic event in both gravitational waves and light, opening a new era of multi-messenger astronomy. However, to everyone's surprise, with the exception of Wince, the gravitational waves arrived 1.7 seconds prior to their electromagnetic counterpart. And there's a reference for that. In the perfect cosmological principle, Return of the Steady State Universe, Wince shows a graphed image of gravitational waves, or gravitons, propagating through space ahead of light, but not because gravitational waves are superliminal, but quote, since the gravitational field is not affected by the nonlinear electromagnetic interaction, the graviton or gravitational waves velocity is precisely c, and the photon and gravitational waves will lose coherence after traveling for a distance. And so there you have it in this video. This is a screenshot showing the gravity arriving at a detector prior to the photons. Since Wince's documentary, several anomalous observations have been made in astronomy. 1. Hubble tension. The universe expansion rate has discrepancies. There's conflicting results depending on whether observations are taken from the early universe via the cosmic microwave background or the nearby universe via type 1a supernova. And as predicted, we should be seeing time passing at different rates at different parts of the universe, which has now been observed. 2. Dark matter discrepancies. Models based on dark-cold matter predict a denser distribution at the center of galaxies is observed. Gravitational lensing surveys of dark matter conflict with estimates derived from the cosmic microwave background. Get to me real quick. The problem with everyone's interpretation of dark matter is the concept of matter. Frank Wilczek properly called it out about 15 years ago when he said, it's not a matter problem, it's an acceleration problem. When dark matter was first observed, what was being seen is that the outer edges of galaxies were rotating faster than they should be based on general relativity and Newtonian mechanics. So what it was is we didn't have a mathematical framework to account for why the outer edges of the galaxies appeared to be accelerating. So the idea was, well, let's just mathematically throw in some extra matter that we can't see, and we'll just assume that that's what's causing it. The only problem is, as our instruments have gotten more sophisticated, they have not seen anything of this supposed dark matter. Yet, if you just apply three-dimensional time to cosmology, you can account for dark matter by simply being a phenomena that's a byproduct of time being multidimensional. The CMB anomaly, the cosmic microwave background, lacks correlation at large angular scales. Dipolar asymmetry in the CMB temperature suggests a violation of assumed statistical isotropy and homogeneity. A large usual cold region in CMB can't be explained without the standard model. Mature galaxies existing much earlier than predicted by current models, some researchers to propose the universe is twice as old. Universe time slowing down. Astronomers have observed time appeared to slow down in the early universe, specifically about 5 times slower than it does today. And we need to come back to this number 5 a little later. The observations of GW170817, Hubble tension measurement, dark matter discrepancies, CMB anomalies, and the universe appearing twice as old and time appearing to run 5 times slower are all consistent with Wince's 3T model. So what's funny and what I got a lot of flack for is basically what I argued is, since I can account for most of these anomalous cosmological phenomena using three-dimensional time, especially redshift, what I argue was the Big Bang Theory is a false theory because it's built off of a singular time dimension. As a matter of fact, what I would say is that you can think of the Big Bang as a temporal vanishing point, right? So like right here on this grid, you can see how. So on this grid, what you can see is everything's converging to the single point, right? But the grid goes on. You know what I'm saying? Like this grid would not just end there, it would just keep going. So the idea I'm proposing is that what the Big Bang actually is is a temporal point of which we can see no further back, because what happens is electromagnetism and particles decay once they go 13.7 light years away from a source, a billion light years from a source. So my argument is that the universe is constantly in flux, vacuum fluctuations at different rates of the passage of time, coming and going. We're in a giant, essentially infinite soup. It never began, it never ended. It just is, right? And that's essentially what you can think of as a steady state model, as opposed to there was a beginning and someday there'll be an end. I'm just going off the assumption it never began, it never started, it just is. So, and that's what the data, and that's what all the cosmological data is pointing towards, is that the Big Bang is a failed theory. Every one of the Big Bang predictions is failing. It's a patchwork of how do we explain away an observation and then glue it all back together in what's called the Friedmann equation. Problem is they've made so many adjustments to the Friedmann equation, they've pretty much destroyed it. The big irony, though, is if you just swap out temporal components for the spatial components in the Friedmann equation, you actually get answers that match observation. So let's go ahead and go to video 7.
There are so many crises in cosmology now. I could talk about a new crisis development every day. The most reported crisis has been the Hubble tension. The data from the early universe, like the cosmic microwave background, gives a smaller value than those from nearby later data, like quasars or supernovae. And as the data have become better, the discrepancy has grown, not gone away. The second crisis in cosmology is that the cosmological principle just isn't correct. This principle assumes that the universe is on average the same everywhere, and it's one of the assumptions for the current standard model for cosmology. Indeed, we can use this model to calculate just how large the biggest clumps of matter should be. The trouble is that astrophysicists keep finding clumps that are bigger than they should be. If our theories were correct, then these large structures shouldn't exist. Another piece of evidence against the cosmological principle is a discrepancy between two measurements of our own motion through the universe. The standard cosmological model tells you what this distance is. But if you use that, then these two measurements of our own motion disagree by almost 5 sigma. The third crisis is that the James Webb Telescope has discovered big galaxies that were around when the universe was only a few 100 million years old. These galaxies appear surprisingly massive and mature for their age. As we discussed in an earlier video, this was a prediction of modified Newtonian dynamics, but astrophysicists have trouble accepting this explanation. They've since proposed multiple alternative explanations that fit the cosmological standard model with dark matter. You can tell that this is a crisis just by noting that they came up with these explanations after the data came in. The fourth and final crisis is the sigma 8 crisis. This is another discrepancy between measurements from the early and late universe, but this one is about a parameter, that's the sigma 8, which measures how much matter clumps over time. Basically, it hasn't been clumping enough. The interesting thing about all these crises in cosmology is that they only came into focus in the past 10 years or so. Astronomers from the University of Sydney have found evidence that time ran slower in the early universe. When we look back in time, we see everything happening slower. It's called cosmological time dilation. Indeed, the two things go together. They were able to infer that about 12 billion years ago, time in the universe ran 5 times slower than today.
You know what's really ironic about Sabine talking about all that? Is recently someone, in my opinion, tried to plagiarize some of my three-dimensional time modeling, making a bunch of wild claims with their alleged 3D time model. And she did a video that she was so angry she threw the guy under the bus and absolutely started cussing and talking trash on the concept of three-dimensional time. So how appropriate that we're now going to roll into some of her complaints about this other guy and actually show how this is done. So go ahead and go to the document. All right. Gravitational waves, light, and temporal discrepancy in 3T. In classical general relativity, gravitational waves and light propagate at the same speed, c. However, observational data, such as from GW170817 and other multi-messenger events, suggest that gravitational waves may arrive slightly earlier than their associated electromagnetic counterparts. This discrepancy appears to increase with distance, suggesting a systematic cosmological scaled phenomena. How 3T resolves the gravitational electromagnetic timing discrepancy. In the 3T model, all physical processes are embedded in a vector space of time. So here we're treating periods, present, and passage all as a singular temporal vector. Gravitational waves propagate primarily through the passage vector T3, proper time, which is aligned with global space-time curvature. Electromagnetic radiation, light, propagates with significant dependence on the time plane, which governs phase coherence and oscillatory propagation. Thus, over cosmological distances, gravitational waves, less reliant on oscillatory coherence, travel shorter geodesics in three-dimensional time. Photons, bound by phase constraints in the time plane, experience temporal dispersion or interference effects from the large-scale curvature of T1 and T2. The effective light arrival delay grows with distance, not because photons are slower than c, but because their projected arrival is smeared along T1, which is not flat on cosmic scales. This projection mismatch is perceptible only at large distances, explaining why it was not observed in local systems but becomes statistically significant for extragalactic events. Implications for the cosmological crisis. The cosmological crisis refers to tensions between different measurements of the universe's expansion rate and age, particularly the Hubble tension, the discrepancy between the early universe and late universe measurements of the Hubble constant, and the age discrepancy. Certain globular clusters appear older than the universe as predicted by the lambda CDM under general relativity. In other words, the Big Bang Theory is dead. Dead as it gets. Apparent cosmological crisis explained. In 3T, or three-dimensional time, temporal curvature increases over cosmic distances. The passage vector warps differently for gravitational and electromagnetic signals. Cosmic time measurements that assume one-dimensional time overlook delays induced by oscillatory dispensation in T1 and T2. This leads to inconsistent calibrations in redshift to time conversion, resolving the Hubble tension without invoking exotic energy components or early dark energy. Time slowing in intergalactic space. 3T posits that local time is the net of oscillation rates in T1 and the present interface T2. In intergalactic voids, quantum vacuum modes decouple, reducing oscillatory phase coherence. As a result, the clock rate in voids slows down, akin to gravitational time dilation, but derived from temporal curvature, not mass energy. This predicts an effective slowing of time in intergalactic space, observable as anomalies in standard candlelights and galaxy distributions. universe appearing twice as old. If the net rate of time passage in intergalactic space is slower, while our local time is faster due to coherent oscillations in dense matter regions, then cosmic history appears stretched when interpreted using local clocks. Events like recombination or first star formation seem more distant in the past than they would if measured in universal proper time. This naturally explains why the universe appears older than predicted, especially when analyzed through photon-based data rather than matter-based records. The three-dimensional time model provides a coherent, geometric explanation for the early arrival time of gravitational waves compared to photons, the growing temporal discrepancy with cosmic distance, the cosmological age paradox, Hubble tension, and perceived slowdown of time in voids. By replacing one-dimensional time with a curved temporal manifold, three-dimensional time avoids invoking exotic new energy fields or hidden particles. Instead, it reinterprets temporal propagation as a geometric feature testable via arrival time differences, redshift anomalies, and potentially observable in the future high redshift multi-messenger events. Observer-dependent redshift and frame inversion in 3T and Existics. An inertial observer in 3T perceives light as redshifted due to extended temporal geodesics. From the photon's own frame within 3T, the universe appears blue-shifted due to inverse phase loop contraction. The Existics framework of relative frames of reference allows both observations to coexist without contradiction. This preserves energy conservation and Lorentz invariance within the curved manifold of 3T. All right. So now we'll go ahead and go back to the original document that we were on. All right. So now what we're going to do, something a little technical, and I'll go through it relatively quick. What we're going to show is that I can actually derive the unit circle by simply plugging in the imaginary number into the Existics equation and using what I call the 50-50 expression, where we're basically assuming A and B are equal. So here we're going to let A equal B equal the imaginary number. We're going to go ahead and follow the rules for N star and U star. And then we're going to go ahead and simplify both and solve for the product. And what we end up with is that when we multiply U star and N star together, they equal 1/2. When A equals B equals I, the Existics recursion formalism naturally reduces to a forward time projection with a negative imaginary component, a reverse time projection with a positive imaginary component, and when multiplied together, the imaginary parts cancel, leaving exactly 1/2. This reflects a deeply meaningful structure. The complex components form a unit circle conjugate pair. Their symmetry product is a real scalar, 1/2, which reflects the spin 1/2 nature of Existics identity evolution. This is one of the clearest validations of Existics as a spinor-like temporal algebra and may directly tie into the three-dimensional time projection basis for unitary evolution, probability amplitudes, and quantum phase geometry. Who would have ever anticipated a series of recursive algebraic expressions being able to go this deep into physics? So let's continue. Interpretation of I. Well, the square root of I equals 1 over the square root of 2 plus I over the square root of 2, which we'll put in the exponential form is e to the pi I over 4. And then the final relationship is that basically u star squared minus n star squared equals I, which equals e to the pi I over 4 squared. The squared difference of the forward and reverse projection yields I. The square root of that difference gives the fundamental quarter turn rotation in the complex plane. This 45 rotation, embedded inside the Existics projection itself, may be the hidden generator of the unitary evolution or spinor phase in 3T. So, in essence, what we've been able to derive by plugging in the imaginary into the Existics equations is a mechanism for deriving the evolution of time from a fundamental and quantum level. All right. So here's the unit circle. And as you can see, we can use the Existics equations to calculate the rise and run. And as the unit circle goes all the way around, we can use the Existics equations to calculate all the points along the unit circle. Just more on the unit circle. All right, so now we're going to see how far we can push this. Not only we're going to let A equal the imaginary number and B equal the first of the quaternions, which is orthogonal to I. So start with our assumptions. We go ahead and plug them in and use our formulation. These projection identity forward and backward between the complex components I and J respectively. The scalar Existics identity constant, so we come in and solve for I. So right here we've solved for I. This is a rational quaternic expression involving a product and inverse. This I is a scalar identity derived from recursive composition representing the overall transformation factor between frames. So here we got our quaternion valued projection to interpret the identity projection as a quaternion valued operator. We define it as such. And here we're going to expand and invert D. We're going to compute the conjugate of D right here. And we're going to solve for the norm. And this is all really just basically quaternion mathematics. So finally, we come down here, the normal and the normalization. The quaternion norm is as follows. And to obtain a unit quaternion, we scale it in such a manner, and boom, this satisfies the unit quaternion. So we were literally able to use the Existics equations to derive 1, the unit circle, and 2, the unit quaternion. All right, so let's keep going. And then here's a summary of the results. And here's the interpretation. The Existics recursion structure projects two complex identity frames, A equals I, B equals J, into a third axis via quaternion multiplication, I times J equals K. The scalar identity constant I encodes the recursive composition of identity under projection. The quaternion valued projection, IQ, represents a directional operator fully consistent with unitary transformations and rotations in quaternic space. So basically, we can use quaternions to describe phenomena in three-dimensional space where your conventional Lorentz transformation or Pythagorean theorem might not apply. Basically meaning you need to use hyperbolic space. This shows that unitary evolution, spin structure, and orthogonal identity axes can all emerge from the arithmetic of recursive Existics projection. Deriving the unitary evolution operator from recursive Existics time steps. So this is where stuff gets really deep. Now we're just going to get into the weeds and derive quantum mechanics fundamentally from the Existics equations. Recursive basis and existics identity space. So again, the same expressions. For these, we construct the identity constant. Again, same thing. And from the existics identity differential, here we bring in this expression. This expression is significant. It corresponds to a pure imaginary unit representing a phase shift of pi/2 in the complex plane. Formalizing a time evolution operator. Now let us interpret this expression in the context of unitary evolution in quantum mechanics, where the evolution state psi of time is governed by the unitary operator. So here's the unitary operator in relation to time, and here we have the unit circle and its imaginary component. When h hat is where h hat is an emission operator, and u hat must preserve the norm of the state vector, i.e. be unitary. Now suppose existics recursion defines discrete time steps delta t equaling 1. Then we propose that when we bring the unitary circle expression and the operator in together, what we end up with is basically a discrete unit of time that we can use for generating time evolution. Thus, the identity differential between n star and u star directly defines the unitary step operator u hat sub e for existics. Recursive time step evolution. Recursive time step evolution in Hilbert space. Now we can define the evolution of an abstract state, psi of t, as the following. Substituting in I, negative I, for the existics operator, this expression is consistent with norm preservation, unitary phase shift of pi/2, first order recursion across discrete temporal steps. So what this means is we can quite literally use the existics equations to create a gradient of time evolution that's consistent with the Schrodinger equation. All right. So here we have our recursive generator as an effective Hamiltonian. We're getting really deep into the weeds on physics expressions. The existics Hamiltonian emerging entirely from the recursive identity arithmetic, not from classical dynamics or energy-based postulates. This gives a novel interpretation. The identity differential is not a quantum potential or energy, but a generator of recursive phase. This recursion defines the temporal derivative of quantum states. So now we'll go ahead and reformulate the Schrodinger equation, taking into account the existics form, and here we have it. Thus, from the arithmetic recursion steps alone, we recover the Schrodinger equation, the unitary evolutionary operator, and the phase generator, all from purely algebraic identity systems. So what does it mean if I'm able to use the existics equations, derive three-dimensional time, apply that to general special relativity and quantum mechanics, and actually bring all these theories together under one consistent set of equations? What would we call that? I have no idea. All right. So the interpretation is the identity projections n star and u star define a recursive algebraic phase. Their squared difference act as a discrete time evolution operator. The result is fully unitary and consistent with the structure of quantum mechanics. No postulates of classical motion, energy, or Lagrangian mechanics are needed, only the recursive arithmetic of identity. And so the conclusion, The Existics identity recursion not only predicts normal preserving state evolution, it constructs the unitary operator directly from algebra, making it a minimal but complete origin of quantum dynamics. All right, so now let's get a little out of the thick math and let's go ahead and jump into, let's see, let's do video 5. Yeah, you're fine. Probably need to reboot it or something. Five.
Relativity and quantum mechanics come together in a unified form in this marvelous equation of Dirac, the Dirac equation, and that marriage of relativity and quantum mechanics gives us two children, spin and antimatter, which you're about to see just now. Here the beta matrix is 1, 1, negative 1, negative 1, and the E is multiplying the identity matrix. And the eigenvectors are simply going to be column vectors with 1 in one slot and zeros and everything else. And when you put in, the constants here, the eigenvalue for the energy for this one's MC squared, minus MC squared, minus MC squared. So you can see that the particle solution split into two kind of particles, one particle with positive energy, one particle with negative energy, and that we're just going to point out here, we have two kinds of solutions in terms of the energy eigenvalues. Here is one pair of solutions, and here's the other pair. So the first pair is your electron with two states, spin up, spin down, and the second pair would represent your positron with two states, spin up, spin down.
If we look at these disregarded phases, what we can see is that because of the double negative sign, Q star would have an equivalence with psi, and Q would have an equivalence with psi star. Based on the peculiar relationship with complex conjugates in a complex plane, the identity between Q and psi star and Q star and psi can flip and reverse all the way around, creating our time loop for the evolution of time. And so based on this mechanism here, we can reaccount for the negative energy or antimatter phase of the Dirac equations with these missing phases rather than the so-called missing antimatter. This can all be simplified through the use of a spinner. To illustrate the symmetry of a spinner, we'll use a small plate with a wine glass placed on top. While rotating my arm around in a circle in order to bring the plate and wine glass back to their original orientation, the plate and wine glass must undergo two complete rotations. The simple properties of a Mobius strip can mnemonically give you an idea of how the temporal loop spinner will be set up. It demonstrates a beta decay-like and anti-beta decay-like process caught in a temporal loop. This loop represents a single hydrogen atom-like structure trapped between forward and reverse time, but cycling in the direction of the arrow of time.
So the basic idea is that we need to apply forward and reverse time to the atom, meaning there's not just two charges, positive and minus. We have four charges: positive forward time, positive reverse time, negative forward time, negative reverse time. And the idea is that inside the atom, we have both matter and antimatter, particles and antiparticles oscillating in and out of phase, but in opposite directions of time. So the idea being is, well, where's all the missing antimatter, right? Actually, it's right here. It's just that because we're only using a singular time dimension, we're not able to create the rotation symmetry structure whereby we could have phases going forward and reverse time simultaneously with matter and antimatter as the base structure for matter. All right. So now we'll go over to this document. This is a document I made quite literally 23 years ago. And this is where I was working out having particles come out of the vacuum and get trapped with one another such that they get caught in a time loop, are not able to go back into the vacuum and form what we know as stable particles. And what I want you to notice here is that I've got a rotation happening here. I'm going to rotate this matrix 90 degrees in relation to this matrix. What ends up happening is I get a combination of quarks here, a combination of opposing quarks here, forward time, reverse time. These cancel out because those are unstable combinations. They decay. And here we end up with 2 protons, 2 antiprotons. Let me read this. The proton is positively charged, thus half of a dipole or dyad. Therefore, it must beget its complementary half in order to balance symmetrically with the background vacuum. The neutron has a greater mass than the proton, thus there exists an imbalance of mass between the neutron and the proton. The proton is positively charged and the neutron is neutrally charged, thus there exists an imbalance of charge between the proton and neutron. Therefore, their masses and charges must be balanced. This is done by the manifestation of the electron-positron and the neutron-antineutron pairs. The neutron-antineutron cross-symmetry balances and the mass differences between the neutron and proton. The electron position balances the charge differences between the neutron and the proton. The means by which this happens can be illustrated through nuclear fusion and beta decay. So the idea is that basically what happens is we'll have an event where a neutron pops out of the vacuum. It only wants to stick around for about 15 minutes and go back into the vacuum. But if we can have it configure with another neutron in just the right way and rotate them in relation to one another 90 degrees, what we're able to do with the 2 neutrons, neutron-antineutron, is that cross-symmetry can come in, they can swap parts, and what we end up with are 2 protons and 2 anti-pi mesons. The pi mesons decay, and what we're left with is a proton-antiproton. So what this is particle production from the vacuum using time loops rotated 90 degrees in relation to one another to create a stable particle, aka a proton, out of nothing. So obviously this and the Big Bang don't really go well together, because I'm arguing that particles come into existence simply through quantum fluctuations and statistical probabilities of certain configurations to happen, certain phases to occur, right? And that's happening all the way into the past and all the way into the future, and that there was no beginning or end. So obviously, if I'm going to push and promote this, I had to find ways to take my model and match it not only to the standard model, but see, was there anything inside the standard model that didn't match experiment, but matched my model of a steady state universe versus the Big Bang. So let's go ahead and go to video.
There was no way of avoiding making specific predictions about the Higgs boson. This was unsettling at the time because the LHC wasn't near completion and wouldn't be up and running for nearly a decade. Besides other exotic predictions, it appeared to me that the Higgs particle should not decay into leptons or quarks easily, if at all. The Higgs should behave similar to the relationship between Z, W+, and W- bosons.
Even though we don't know which theory governs the behavior of Higgs bosons, or if they even exist at all, we understand very well what the Standard Model predicts about the Higgs boson. The Higgs boson is on the left, while there are 5 other particles arranged in a column on the right. They are the most common particles into which the Higgs boson can decay.
The new goal was to find a way to match my new prediction to the Standard Model in the event I happen to get it right. With the big announcement that's going to be made on July 4th, I really doubt that they're going to come out with the big grand announcement of finding the Higgs particle and finding it in such a way that it satisfies all of the expectations. A more complex concept of the Higgs particle would be needed.
The inclusion principle and the exclusion principle become interlocked in a temporal oscillation of the one becoming the other. Distinguishing one particle from the other becomes a point of quantum behavior. Through the inclusion and exclusion principles, in a cross-symmetrical fashion, particle and antiparticle identities exchange, oscillating in and out of identity crisis moments in 3 dimensions of time.
If we combine the ZZ and gamma gamma, a combined significance of 5 standard deviations.
You have an excess of one big spike here in this region here.
As a layman, I would now say
we have bagged the Higgs boson.
We have observed a new particle consistent with a Higgs boson. Which one? That remains open.
The Higgs was exhibiting identity crises between the decay channels of the Atlas detector and the CMS detector. This indicated entanglement between the Higgs phenomena in both detectors. So this would indicate that the Higgs to gamma gamma channel has more mass than the Higgs to ZZ channel. And then it's the ZZ channel now that's more massive, and it's the gamma gamma channel that's lighter.
How about that?
The Higgs to ZZ channel has the heavier mass here, and the Higgs to gamma gamma has the heavier mass here. What's your opinion about that?
Well, it could be a resonance phenomenon. So this is count at a certain energy.
Yeah, exactly.
Okay.
They're not showing any coupling with the leptons or the quarks.
Well, that's right, yeah. It's just going to bosons there.
So we could correspond the masses like this. The problem here is that we have one particle and 2 detectors at the same time in both instances, which is extremely peculiar and odd. So what's the alternative? And that is to go, okay, well, what we have is we just have a single Higgs particle, but there is a mass variation that's happening with its decay modes. The problem with that is then we have to explain not only why there is a significant mass difference between the gamma gamma and the ZZ channel, but why that reverses between the detectors. It looks like we're having sort of a quantum behavior of do we have one particle or 2, and it looks like it depends on how you measure it.
So the issue was actually a resonance phenomena and some sort of a correlation inside the ring where you would get correlation between what's detected here and detected there, and there's this observable some sort of phase phenomena between the two, so that there could be new phenomena of the protons circulating in there.
So for there to be entanglement between the 2 detectors actually isn't that peculiar at all then, is it?
No,
it's unexpected, but it's not peculiar.
It could, each proton could have a wave function inside the ring.
Well, what have we actually measured as of July of last year? We measured these guys with pretty good detail. We made some measurement of these guys, but they weren't all that accurate. And that's where we stand. We didn't measure this, we didn't measure this, we didn't measure this, didn't measure this. And these are the things as of July 2012, what we measured. Nothing that we measured showed it to be wrong, but that doesn't mean that it was right. So here's Atlas, here's CMS. This is data measurements. Now, what should it look like? If the Higgs boson didn't exist and everything was perfect, we would see the data along this left-hand line. If the Higgs boson existed and it was exactly as predicted, we would find the data on the right-hand line. And again, CMS and Atlas. So that kind of tells you what you should be looking at. And this is what we had talked about. But so if you have to really learn statistics, if you're going to do particle physics, you have to take this kind of data and come up with an answer from it. So there are some options. It could be that this 10 to the 38 GeV thing is wrong, or the Higgs boson has stuff inside it, like a proton does, in which case the standard model breaks. Alternatively, this boson minus fermion thing is equal to 0. And one way to do that is this theory called supersymmetry. This, however, is an absolute screaming idea that no matter what, the small mass of the Higgs boson means there must be new physics, and it's in these two terms.
If we compare the CMS and ATLAS data side by side, we see pronounced twin peaks in both data sets, but with a significant difference. In the CMS data, the ZZ channel is significantly more massive than the gamma-gamma channel, yet in the ATLAS data, it is reversed, with the gamma-gamma channel significantly more massive than the ZZ channel. As of summer 2014, the Higgs paradox was becoming more and more apparent.
That has got to be one of the greatest scientific discoveries that went unnoticed in history. Wrap your head around this. So it's 2012. They start announcing that they're going to start releasing data from CERN regarding the Higgs particle. About 10 years prior, I'd worked out that modeling that I just showed you with the particles coming in out of the vacuum and all this stuff. And in that, I quite literally had very specific predictions that fly in the face of the standard model. So it's really exciting because two things were going to happen. Either I was completely full of shit and I could finally stop doing Existics for, because this has been going on for over 30 years. Or actually, I would have gotten it right and something would have come of it. Well, what came of it was CERN and ATLAS started actually censoring their data and hiding their results, and we haven't heard anything about this since. Here are the big takeaways. The Higgs didn't couple with any of the massive particles as was expected because the entire purpose of the theoretical Higgs particle is to explain mass in some of the particles, but it didn't couple to any of them. What it did instead was coupled to a bunch of what are called exchange particles, bosons, photons, W and Z particles, which is exactly what my model predicted, because this is essentially based off of things coming out of the vacuum and going back in, so that you could think of the vacuum state as the creation and ending of things, boundary of reality, right? So my model had the Higgs fluctuating in such a way that quite literally matched the data, and I was pretty shocked by this. So let's go over this paper right here. The Higgs mass discrepancy as evidence of M symmetry breaking. What M symmetry essentially is you have, so let me go through this. Well, you know what? Let's go to the M violation video. That'll explain it. So video 10.
Symmetry plays an important role in the mathematics of physics. For every left, there must be a right. For every up, there must be a down. For every front, there must be a back, and so on. In quantum mechanics, the principal symmetries that support physical law involve charge, parity, and time. Charge conjugation symmetry corresponds with reversing electric charge and all the internal quantum numbers. Parity symmetry corresponds with space inversion, reversal or flipping spatial coordinates, and time symmetry corresponds with reversing time derivatives. Together, charge, parity, and time form the symmetry physical laws are built around. Since CP violation and T violation have equivalence, since mass can be shown to be composed of temporal components, and since charge conjugation and parity can be projected into three-dimensional time as scalars, we can apply a four-vector model generating CPTM symmetry.
Turns out if there were no CP violation, then all of these would be along the real axis. And so somehow the area of the triangle is measuring the amount of CP violation.
With this dimension of time corresponds here to both A and B having a change in their passage of time. If we examine the mathematics for measuring decay rate, the decay rate can be associated with the periods of time component, and the mean lifetime can be associated with the passage of time component. Since the base expression for mass equals the absolute value of t prime times t squared, there are two possible observations. First, we are dealing with decay rates of time, so we can set the passage of time as the vertical component for both b minus b asterisk and a asterisk minus a. On the other hand, we are using a model compatible with massless particles, so we can set the present time as the vertical component for both b minus b asterisk and a asterisk minus a instead. The first corresponds with massless particle propagation, and the second corresponds with inertial mass and momentum. Time reversal asymmetry is equivalent to a charge parity asymmetry. If we take both types of time reversal asymmetry, where the passage of time coordinate values are inversely proportional to their corresponding linear time values, we can argue that charge parity asymmetry and time reversal asymmetry are indicators that CPT symmetry is incomplete as a fundamental symmetry of physical law. The basic existics equations can account for mass invariance using 3 dimensions of time. So how do we account for an invariance or break in this symmetry? M violation. What is M violation? Since charge parity and time reverse symmetry are equivalent, charge parity and time reverse symmetry together in this 3-dimensional time model is equivalent to mass symmetry. M violation becomes central to the quantization of gravity. If we assume Einstein's equivalence principle, a variance in acceleration or mass would indicate an inequality, and t squared could not equal 1. However, if the two masses are significantly different, then t squared can have different values relative to different rates of the passage of time in correspondence with each mass, without violating Einstein's equivalence principle.
That's just stunning. I mean, to just put it frankly, M symmetry is how I've got modern physics by the balls. Because the problem is they've locked themselves into what's called the 4 vector. They've limited themselves to 3 dimensions of space, x, y, and z, and 1 dimensions of time, t. And with those parameters, they only have the ability to have charge, parity, and time symmetry. They don't have enough extra dimensions or scaffolding, mathematical scaffolding, if you will, to do extra rotations to account for extra phenomena, right? Well, I bring the extra time dimensions in, which means I have to have an extra symmetry. And since I'm accounting for mass as being temporal in nature, then what I should be looking for is a break in charge, parity, and time symmetry that has something to do with mass, and that would prove that M symmetry is an extra symmetry that has to be applied to physics. So now we'll go ahead and go to the Higgs document. The Higgs mass discrepancy and evidence of M symmetry breaking. When the Higgs boson was discovered in 2012 to 2014, both ATLAS and CMS measured its mass in multiple decay channels. And here's the experimental data. Notice they didn't have much data on gluons or leptons. They just had data on the Z and the gamma, which is exactly what I had predicted. So this is ATLAS's data. This is CMS's data. And what I want you to notice, which caught my attention, is that notice so these are photons, right? So this is the channel where they measure photons. This is the channel where they measure the Z particle, which you can think of as a very heavy photon. Notice the mass in the gamma channel is approximately 124 GeV. Up here, it's approximately 126. Yet the Z channel here is approximately 124, but down here it's 120. So notice they flip. Where the gamma is heavier than the Z is heavier than the gamma, and vice versa. And I didn't see that as a coincidence, because what's interesting is both the CMS and Atlas detectors are quite literally around a ring, right? So you've got all these protons going around the ring. They're going to be colliding. And what's crazy is that if you think about it, right? If they're making measurements at opposite sides of the ring, and we've accelerated protons to near the speed of light, and they're entering into a plasma state, we should expect to see some kind of phase phenomena, some kind of unexpected coherence that would show up as an interference in the data. That, in my opinion, should have been expected. So let's go down here and look at the data. So if you look right here, this black hyperbole right here, this is what it was supposed to do experimentally. But what it did was it bifurcated into a heavier and a lighter channel. So the way they got away with this is they literally just averaged these out together to make it fit theory. So wrap your head around that. Modern physicists will take their data and fit it to a model to prove the model is true. Does that sound right to you? No. Because to me, obviously, something else is going on. And you would think physicists would be excited to see, oh, wow, look, something new. No, see, they don't want anything new. They hate new. What they're trying to do is they're trying to just cinch the thing, wrap it up, call it a day. We know everything there is to know about physics, and move on. Only problem is the universe is really good at constantly revealing to us we don't know our head from our ass when it comes to the totality of everything. So I always find it funny that the universe constantly throws us an experimental anomaly that we then get a new mystery to study. At any rate. So again, here's the data. I put them both together so you can see that in CMS, what channels? I can't read it from here. At any rate, you can see how the data switches, so on and so forth. So why is this anomalous? The Higgs boson is a scalar field with no internal degrees of freedom that would produce such systematic channel-dependent mass shifts, meaning there's nothing in the theory of the Higgs boson that would do such a thing. Systematics could, in principle, affect one experiment consistently, but not two experiments in opposite channels. In other words, Atlas sees gamma heavier, CMS sees Z heavier. This raises the question, is there an underlying dynamical effect sensitive to decay channel coherence? 3T interpretation, temporal phase projection. In Wince's 3T framework, all mass arises from temporal curvature along the passage coordinate. Decay channels correspond to different temporal loop projections. The gamma-gamma decay channel is sensitive to the electromagnetic projection of the temporal spinner. The ZZ decay channel is sensitive to the weak interaction projection. Because temporal loops can have non-commutative holomony, the same state can appear with slightly different effective temporal curvature depending on how it is measured. Holonomy. This is M symmetry. A small rotation on the temporal loop alters the projection of curvature mass in the decay channels. So here's a quantitative estimate of the mass discrepancy. So recall the temporal curvature function, and notice this takes on the form of the Pythagorean theorem, where this symbol are 8 eigenvalues associated with T1, T2, and T3. So basically, you can think of this as one clustering of T1, T2, and T3, and this is another, and we're going to solve for the curvature between these two temporal positions. Suppose the two decay channels couple to slightly different effective temporal phase vectors, right? So here's for gamma, here's for z. Then the mass difference would essentially be this, and it would be proportional, right, and approximate. This shows that even a tiny residual phase shift in T3 generates an observable 2 GeV mass difference. So basically, as one is phase shifting one direction, the other is phase shifting the other direction as the measurements are made, collapsing the probabilities down to the observable. And that's why we're seeing a coherent measurement between the two detectors. Significance of the swap channels. Why did Atlas and CMS see opposite assignments? 3T suggests each experiment's measurement protocol may couple differently to the temporal phase. The projection can be positive or negative depending on detector timing and phase locking with the field modes. This is exactly the behavior you would expect if the temporal spinner of the Higgs has small residual M symmetry torsion and different decay channels probe different projections. And so here's a table showing the swapping as was predicted, because this gets into my concept of cross symmetry and identity crisis. 3T interpretation. Temporal loop projections differ between decay channels. And M symmetry breaking produces channel-dependent effective mass. Swapped patterns across experiment consistent with coupling to residual T3 torsion. And that's basically it. So the Higgs data actually matched a three-dimensional time model of particle pair production coming out of the vacuum, getting stuck in a time loop as being the source of matter versus the Higgs being a particle in the standard model that brings mass to all the other particles. So basically, I don't know what to say about the Higgs other than that was one of the most forced experiments interpretation of their data I've ever seen in my life. All right, so now let's go to, let's see. So I'll go ahead and go back to this document. All right. So here's another fun one. This is one of my favorites. Using recursive expressions to resolve self-energies. So in quantum mechanics, they've got this problem where when they try to take all of the different possible paths that a particle can do to add up its probabilities, that all has to fit within a value of 1, right? The total probabilities can't exceed the value of 1. Think of it as like 100%, right? You have 10% this possibility, 20% this possibility. So when you add up all the possible outcomes, it should give you 100%. In the same way, because we're using a unit circle in complex numbers in quantum mechanics, all the probabilities have to add up to 1. So background, the self-energy problem in QFT. The self-energy problem is that when they add up all the self-energies of a particle interacting with itself, even though those are really small incremental possible additions of energy to the system, the problem is because they're using summations, they end up having the equation go to infinity, so it's meaningless. So they have to do this technique called renormalizations, where literally they cut all the infinities out of the equation and make them work. So not only do we see physicists fitting data, but they'll go so far as to take a hatchet to their own equations, chop the infinity off and say, voila, it works. That's not good math. All right, in quantum field theory, the self-energy of a particle arises from its interaction with its own field. This leads to the integral over loop diagram that diverge at high energies or ultraviolet divergences. So basically, when you try to add up all the different tiny little loops that can happen with self-energy interactions, the equation goes to infinity. So renormalization procedures are induced to subtract or absorb these infinities into redefined physical constraints such as mass and charge. Though effective, these procedures lack an underlying arithmetic or geometric justification and are often considered conceptually unsatisfying because you're not doing math. Suppose a particle's observed energy is the sum of its bare energy, E naught, plus its interaction with its own field, which depends on that energy again. So we'll take E naught, the bare energy, plus the looping back in on itself, and that gives us our effective energy, right? Well, that's a geometric recursion, not an infinity. So notice by bringing the Existics equations in here, as long as we don't have aleph equal 1, this equation doesn't go to 0 and it doesn't go in infinity, it converges. Right? So Existics recursive framework, a non-divergent alternative. Existics theory defines identity relationships via recursive arithmetic expressions, yada yada. Showed you guys this several times already. In this system, identity is not statistically defined, but rather dynamically projected through recursive deviations between forward and reverse pathways. These expressions avoid divergences entirely by working within finite dimensionless arithmetic. So, quantum electrodynamics predicts divergence logarithmically or quadratically, right? Instead, model it recursively. So we'll let E naught be the bare rest energy, aleph be a coupling constant, i.e. the fine structure constant, where this symbol is delay from the recursive interactions across T1, T2, and T3, not physical space, but time depth. This automatically bounds the growth of E without any arbitrary subtraction. Reformulating self-energies as a recursive identity, let M naught be the bare mass and suppose interactions with a field add a recursive contribution to mass via bink, adding a little bit onto there, right? Where epsilon M is the self-energy correction depending on the current mass estimate. This resembles the form of n to the sub n plus 1, right? This was the first iteration from n naught. And remember, we'll go n1, n2, n3, etc. If epsilon mass is linear or approximately as such, we can define the bare mass plus the self-energy mass as such. This is the same structure as the Existics fixed point. Rather than removing divergences, Existics defines finite recursive fixed points whose value depend on the relational geometry of input parameters. So one of the big differences, if you look at the Existics recursive equation, I'm dividing into a denominator that keeps getting divided up into smaller pieces. I'm not adding an infinite series of summations that has the potential to diverge to infinity. So basically the trick I did is I buried the infinity within the algebra as a recursive equation, and because I was able to do a substitution, I'm able to get a simple algebraic expression that means the same thing. But I don't have all this mess with all these infinities I need to get rid of because they're buried within the expression itself. So, if the bare energy is the core energy and B is the field feedback divisor, then boom, we get a finite expression. This implies that recursive self-interaction yields a finite effective energy providing feedback that is dampened by recursion, not looped instantaneously, And we don't need to do that stupid renormalization and cutting infinities off to pretend we're knowing what we're doing when we just have been using bad mathematics for quite a while. All right. So in Existics plus T3, a particle's self spans temporal loops. Interaction with its own field occurs across these orthogonal time axes. Each self-interaction is delayed and frame relative. And they're not all instantaneous because I actually have a time evolutionary operator in the Existics form of quantum mechanics where these are sequentially spread out rather than dogpiled all on one instantaneous moment. This creates a nested energy recursion tree, and at the limit, if B sub k is greater than 1, the product grows, this series converges, and the energy will always be less than infinity. Thus, self-energy in 3T recursion always converges because it is delayed, filtered, and nested across independent time channels. Finite self-energy differential without renormalization, and there you have it. That looks a lot better, doesn't it? I'm just simply using the Existics equations and applying them to time evolution and quantum mechanics, and I don't have to do the renormalization of the self-energies of the path integral. All right. So this represents recursive distance from linear proportions. And again, I think the picture's being made pretty clear. This difference reflects the nonlinear feedback induced by recursion. It quantifies the curvature between recursive projection and the internal coupling. Together, the self-energy gives us this expression, which is always finite, always converges, and is actually quite beautiful when you look at it. This total expression captures a self-energy-like correction to the identity frame without requiring any renormalization counterterm. So as you can see, it's a much cleaner approach. Conclusion, the Existics framework resolves self-energy divergences not by subtracting infinities, but by redefining identity as a recursive convergent process. In doing so, it establishes a new arithmetic basis for quantum corrections, one that may be extended to renormalization-free formalizations of field theory, quantum gravity, and temporal self-consistency. All right, I'm going to blast through this one pretty quick, but I think you guys are getting the idea. It should be pretty apparent that I'm deriving physics from Existics, going back to my original claim that basically physics is a subset of existence, and Existics is the study of existence. So obviously the rules in Existics are going to be more general than the rules in physics. All right, quantized spin derived from Existics recursive arithmetic. So as you can see, we're going back to our unit circle expression. And what's really neat is that when we go to solve for A star and B star, look at the solutions we get. Now this is wild. Why two solutions? Well, because the Existics structure forms a second degree identity relation forward and reverse projections, meaning we got a projection of A forward, we have a reverse projection B. So now we'll come down here and we'll shift it. The Existics structure forms a second degree identity relation forward and reverse projections relate as such. Hence, the two solutions for each identity projection correspond to one forward in phase, one reverse, 180 degrees out of rotation. And I just want you to look at these values right here that just popped out of these expressions, okay? The existing identity projectors, right? From the prior derivation, we got this, right? These values arise from the following, right? Where we derive the 1/2. Well, here's what's crazy. We're going to go ahead and construct a metric vector and put all these values in that metric vector. We're going to have it follow 4-dimensional rules and rotate into observable basis, multiplying the metric vector by the imaginary unit right here rotates the basis into the real line. So by multiplying I into here, we convert all these imaginary numbers into real values. Now, why is that important? Well, the Existics formalization under the symmetric assignment of A equals B equals I produces complex valued identity projections whose rotation real parts via multiplication by I yield a complete, discrete, and symmetric spectrum matching the spin 3/2 representation. This occurs naturally from the arithmetic structure of the Existics equations. No postulates of quantum mechanics or Hilbert space formalism are needed. This result strongly suggests that quantum spin arises as a derived consequence of Existics identity asymmetry and complex phase normalization. Do you realize we just derived all of the charges found in quantum mechanics just simply looking at the Existics equations and just running through the expressions? Background in polar form of complex numbers. Any complex number, Z is a subset of Z, which is an element of C, can be written in polar form as, right? And this represents the polar orientation around the unit circle. The imaginary unit has I equals e to the I pi over 2, right? So expressing the Existics difference in polar coordinates, these are the results we get. Phase interpretation. This means the difference in squared identity projection is a unit norm complex number rotated by pi over 2. That is, it lies on the unit circle at 9 degrees phase offset from the real axis, just like I showed here. Now, something I should mention is notice I'm showing a lot of really complex formalization that is not in any of my videos, yet the videos I'm describing the formalization word for word. Guess why? This is the first time any of these expressions in their complete form have ever been digitized. Up until recently, these expressions that you're seeing up here were literally in notebooks going back to 2003 through 2011. Have fun with that. All right, so we'll go back to our document. All right. This has key implications. The Existics recursion structure embeds at pi over 2 phase rotation and complex identity evolution. The operation u star squared minus n star squared defines a directional operator on the unit circle, aka the arrow of time. We see that we get this, right? Summary in polar form. This confirms that the difference of squared Existics projections is a unit magnitude complex number at angle pi over 2 corresponding to a 90-degree counterclockwise rotation on the complex unit circle, a key structure in quantum phase dynamics and unitary evolution. So quantum mechanics and time evolutionary operator. So real briefly, we'll just go through here and show that we're just going to plug everything in here, and we're going to go ahead and create our discrete generator for time evolution. We're going to apply Planck units, bring in all the conventional notation. This is exactly how a unitary phase rotation evolves in a state in a Hilbert space. So the Existics equations naturally operate within the Hilbert space mathematics. Ironically, though, if you go look at the Hilbert space mathematics, they don't have time occurring. They treat it as though it's stationary or in a single moment. Yet with this, we're actually able to evolve sequentially one unit of time after another. Again, we're just going to shove all this into standard formalization. This confirms that the Existics recursion is norm-preserving, hence unitarity. And that's why we were able to create M-symmetry, because of that preservation of unitary, aka invariance. Interpretation: the Existics recursion step behaves as a unitary operator generator. While embedded in a Hilbert space, it defines a discrete time step evolution. Ta-da! This shows that Existics recursion defines a discrete complex rotation acting as a unitary time evolution operator, preserving norm, consistent with quantum dynamics, and naturally projecting into Dirac-Brocket formalization. All right. Formal operator algebra and Dirac evolution equation from Existics equation. So what we're going to show here is that we're able to basically rewrite the Dirac equation, but in terms of the Existics recursion. We get these quantum evolution operators. This formalization preserves the inner product, yada, yada. The Existics recursion generates a complete face metric identity space. When organized into a transformation set, this space forms a closed system under complex conjugation, encodes both positive and negative phase solutions, projects onto the unit circle under phase rotation. Thus, Existics generates a self-contained identity phase space consistent with quantum rotation invariance. All right, the identity transformation matrix is complete and relational. Existics temporal manifold is natural spin valued. Look at this. It's precisely a set of spin 3/2 eigenvalues. This is just mind-boggling, to be honest. Thus, Existics is not merely compatible with spin algebra, it generates the quantum spin space as a consequence of recursive arithmetic. AKA, it's more foundational than physics itself. All right. So general and special relative... Wait. Oh, now we're going to derive general and special relativity from Existics? All right, this is getting too much. All right, general and special relativity arise from period passage reciprocity. Existics defines three temporal axes. T1 is the period forward identity, yada, yada. We've gone over this stuff before. And here you can see we've got our Lorentz type structure, right? And so, to kind of get a little bit further in here. Here we go. All right, I skipped ahead too far. All right, a temporal curvature field equivalent to the gravitational field. So essentially what we're able to do, and I don't have it drawn out as well as I probably should in this paper, but another video I will do is actually going more into the weeds on general special relativity and deriving them from Existics. But essentially what it is The inverse relationship between passage of time and periods of time that we get out of existics reveals itself as kind of the fundamental concept hidden as a buried assumption, if you will, within special and general relativity. All right. So now for the grand finale, the mathematical, well, there is no grand finale because I've got about 300 papers written on existics. But the grand finale for today's video, the mathematical significance of the existics equations. So remember the whole 10 over 20 thing? I've been showing that off since the 1990s. Well, now I'm about to just drop a massive information nuke. So notice the ratio between 100 A and B, 100 over 20 is 5. How much did they say time seemed to be going by faster in the past? Or I'm sorry, how much does time in the current age seem to be different from time at the beginning of the Big Bang? Wasn't it 5 times? And what's the ratio of matter to the rest of the universe? Isn't it 5%? This is going to be fun. All right, so let's go ahead and do the existics forward and reverse projection for A over B. We get those values. Okay, so these project identity through recursive differential layers rather than static proportions. All right, so here we got our identity constant, differential deviations from reference baselines. Let us define natural baseline, n not equals 5, a clean rational baseline for n star, and u not equal 0.2 rational baseline for u star. We compute, we get our forward deviation, our reverse deviation. Now, form the recursive differential amplification ratio. So basically what this symbol represents is the ratio between the complete differential from n star to n naught or u star to u naught. So we'll put those values over and divide them. This quantity captures how much faster the forward deviation grows compared to the reverse deviation, an identity structural amplification factor. All right, so nonlinear correction via identity squared. So we're just going to go ahead and square our identity constant. And now we're going to do something different. We're going to compare to the forward recursive projection. We're going to introduce a new symbol, delta, equals n star minus I squared, which gives us this number here. This deviation reflects the nonlinear difference between projected identity and recursive curvature. It will be used as a correction term. All right, recursive derivation of the fine structure constant. What? We're going to derive the fine structure constant from the existics equations too? All right, now combine the linear amplification and the nonlinear correction, and this is what we get, 1.137.0715, so on. This expression approximates the inverse fine structure constant, right? So as you can see, this almost looks like the inverse fine structure constant. They're just off by a little bit, right? All right. The derived value is remarkably close. Using only arithmetic recursion, no physical assumptions of units or geometry. We're just playing with the existics equations. All right, so now the number 137 holds a special place in physics. The number 137 is assumed to be the maximum number of elements we can have, presuming the fine structure constant, and the element was better known as Feynmanium, named after Richard Feynman. it is approximately equal to 1 over aleph, the inverse electromagnetic coupling constant. It has been referenced to, that's not aleph, that's alpha, sorry. It has been referenced as to Feynman's magic number or Feynmanium. It is dimensionless and shows up both in quantum electrodynamics and fundamental atomic structure. In our derivation, the value is 137.715 yada yada and is centered closer around the integer 137. This suggests that 137 serves as a symmetric center for recursive identity structures. We compute the centered value by symmetrically reflecting the inverse fine structure around 137. So here's what we'll do. So the true inverse fine structure constant equals the approximate one minus 1/2 times the approximate one minus 137. And this is what we get. And then we're going to invert it to actually get the value that associates with a fine structure constant. All right, so let's compare this to experiment. So here's our calculated derived value for the fine structure constant. Here's the one that's observed in the lab. And notice it's accurate all the way out to this point. So 1, 2, 3, 4, 5, 6, 7 placeholders. That's pretty significant, but it's frustrating that it's not more than 7 placeholders. And for a brief moment, I was a little bit pissed that I did nothing here but just some math magic. But then I noticed something. If I subtract these just to see what the difference is, right? So let's just go ahead and, well, what's the difference if I take the Existics derived fine structure constant and the one from experiment and subtract them? Oh, I get a very interesting number. This number, all right, so if I divide that number by 20, our original B, remember A over B being 100 or 20? Well, let's bring the original 20 from B back. If I divide this by 20, I literally get the baryon asymmetry parameter. Meaning, if I take the fine structure constant I derive from Existics and subtract from it the experimental observed fine structure constant, the number I'm left with, the unitless number I'm left with, is the unitless number that's associated with the ratio of matter to antimatter in the universe. You really can't force this amount of internal consistency. Obviously, what Existics is a new form of mathematics that had never been seen before. And to kind of give you a spoiler, it's a recursive arithmetic for deriving hyperbolic space or hyperbolic curves. So it's pretty interesting to have a simple algebraic solution for some of the more complicated forms of mathematics known. So this quantity characterizes the imbalance between matter and antimatter in the universe. This suggests a direct coupling between electromagnetic structure and baryonic asymmetry, mediating by recursive identity deviations. Note the original ratio was 5. In cosmology, the fraction of visible baryonic matter to the universe is 5%. The coincidence of the ratio in the arithmetic structure tied to the same recursive derivation that produces the fine structure constant and the ratio of baryonic matter strongly suggests the Existics equations encode interrelationships among electromagnetic coupling, matter-antimatter imbalance, visible matter density. So finally, here's a table of all these numbers that we just derived and the expressions that went along with them, the two outstanding being a near value to the fine structure constant that when subtracted by the experimental value gives us a value for the ratio between matter and antimatter. And that 5% of the universe happens to be visible matter, just to throw that in. So the conclusion, the recursive arithmetic structure of Existics accurately reconstructs the fine structure constant, centers its derivation around Feynman's 137, reveals the baryon asymmetry parameter, links the visible matter ratio to the universe, and does so using only dimensionless identity ratios and projections. These constraints are not independent. They are interlocked through identity recursion. So there you have it. I mean, this has been quite the packed video, and I think we've covered everything. I'm looking real quick to see. Oh, well, I mean, there just gets to the point where how much clothes can I stuff into the suitcase before I go on my trip, right? So basically, what's the takeaway of this? What the takeaway from this is, I just presented to you a series of very simple equations from which I was able to derive most of the basis from which physics is built on. Not only that, I was able to derive a three-dimensional mathematical structure that can be applied to physics that made very specific predictions that have now been observed experimentally. So, I don't know, but that's basically it. I've been doing this for the past, I don't know how long, and my brain is completely fried. I wanted to do this video with a couple more documents, but there's just no way. So anyway, thank you for watching, and please, if you want to debate me, argue with me, pose questions, feel free to. I'm open to communication in the chat, and thanks for watching. Gavin Wince signing off.
Every legend has a humble beginning.
In world news, leaders are gathering today for the annual summit.
I want to tell you something, Che. The government is watching us through the television.
Oh, John.
Look, right there. They're trying to hack into my TV box.
We're still not able to hack into the TV box, sir.
Ha! But they can't.
I've rebuilt the entire electronic system, and it sends and receives signals through quantum phase space. They'll never get in. Engage target.
In other news, local authorities are investigating a series of strange atmospheric phenomena reported by residents.
Ma'am, we're with the federal government. We need to ask you some questions.
John?
Is there a problem? We've been trying to penetrate your TV box for over 6 months.
I told you they were trying to watch us through the TV, but you didn't believe me.
We can't get in, and to be frank, we have no idea what you've created.
Yeah, that's the point. It's called privacy. You know what the Fourth Amendment guarantees?
All we know is that we can't get inside. We want to know if you can create one for us.
QUX. Even the government wants one.